Have you ever really stopped to think about how a simple piece of curved glass or a mirror can totally bend reality? You know, how it can take something huge and just shrink it down into a tiny, perfect little image? Well, it's not magic, not at all, it's math. And today, we're going to pull back the curtain and decode the simple, elegant formulas that make it all happen. I mean, think about it. You're driving, you glance over at your side view mirror, and you see an entire bus, a whole bus, in that little rectangle of glass. How on earth does that work? Well, physics has a very precise mathematical answer, and we're about to walk through exactly how that little mirror pulls off such a big trick. So here's our game plan for today. First, we're going to lay down the rules of the road, the basic principles we need. Then we'll jump into the famous mirror formula. After that, we'll figure out how to size up the image. Is it big, small, upside down? Then we'll switch gears to lenses and finish up by connecting it all to something many of us use every single day: eyeglasses. Okay, first things first. Before we can do any of the fun math, we need a universal system for how we measure things. Now, I know, rules can sound boring, but trust me, this is our map for navigating the world of optics. It's called the New Cartesian Sign Convention, and it's absolutely essential. And this is so critical, because without a standard way to define what's left, what's right, up or down, our formulas would be completely useless. This convention makes sure that when I get a plus sign in my answer, it means the exact same thing as when you get one. We're all speaking the same language. So here's the setup, and it's pretty simple. Think of it like a graph. The very center of the mirror, we call that the pole. That's our origin, our 0, 0. The main line running straight through it, that's our x-axis. And here's the key rule. We always place the object we're looking at on the left. That's it. Every single measurement we take starts from that center point, the pole. Now for the part that unlocks everything. It's all about plus and minus signs. Any distance you measure to the left of that center pole is negative. Any distance to the right is positive. Simple enough, right? And for height, anything above that main axis is positive, and anything below it is negative. You got to remember this, because it's going to be super important in just a minute. All right, with those rules locked in, we can now bring out the big gun, the mirror formula. This is the powerful equation that perfectly connects where an object is to where its reflection is going to show up. It's like a recipe for reflection. And there it is. Looks simple, right? But it's so powerful. 1 over v plus 1 over u equals 1 over f. This single, elegant little equation is what governs pretty much all reflections in curved mirrors. But you know, what do these letters actually stand for? Let's break it down. First up, u. That's the object distance. It's just how far the thing you're looking at is from the mirror. And, based on those rules we just learned, since the object is always on the left, u is almost always going to be a negative number when we plug it into our formula. See how those rules are already coming in handy? Next up is v, the image distance. This is where the reflection, the image, actually appears. This is usually the mystery number we're trying to solve for. And here's the really cool part. The sign of v, whether it ends up being positive or negative, tells us exactly where that image is. Is it in front of the mirror, or is it kind of behind it? The math tells us everything. And finally, there's f, the focal length. This has nothing to do with where you put the object. This is a property of the mirror itself. It's built in. It's all about the mirror's curve, and it tells us how strongly that mirror bends light rays together or spreads them apart. It's like the mirror's unique fingerprint. Okay, so now we can find where an image will be. But what about its size? Is it going to be bigger, smaller, the same? And maybe more importantly, is it going to be right side up, or is it going to be flipped upside down? For all of that, we need to talk about magnification. So the formula for magnification, which we call m, actually gives us two ways to find it. We can find it by comparing the height of the image to the height of the original object. But even cooler, we can also find it just by using the distances we already figured out. Magnification is also equal to negative v divided by u. It's super handy. So let's make this real. Let's say we do the math and we find out that our magnification, m, is equal to -2. This one little number is like a secret code. It's not just 2, it's -2. And both the sign and the number are telling us something totally different, but equally important about our image. So let's decode it. The negative sign tells us the image is real and inverted. Inverted just means it's upside down. Real means you could actually project it onto a screen because light rays are physically meeting at that spot. Now, what about the number 2? That just tells us the image is twice as big as the original object. So m equals -2 means an upside-down image that's twice the size. See? Simple. Fantastic. So we've basically cracked the code for mirrors. Now let's switch over to lenses. And I've got great news for you. If you understood the mirror formula, you are literally 99% of the way there for lenses. The logic is exactly the same, with just one tiny, tiny little change. Just look at them side by side. The mirror formula has a plus sign. The lens formula has a minus sign. That's it. I'm not kidding. That is the only difference. Everything we learned about U, V, and F stays exactly the same. We just flipped one little sign. And okay, there is one other small tweak for lenses. The magnification formula, it drops its negative sign. It's just V divided by U. It might seem like a tiny detail, but it's a super important one to get our predictions about the image's size and orientation just right. All right, let's take all this theory and bring it right into the real world. We've been talking a lot about focal length, but if you've ever been to an eye doctor, you know they don't talk about focal length in meters or centimeters. They talk about the power of a lens. The power of a lens, which we write as a capital P, is really just a measure of how good it is at bending light. And the formula could not be any easier. Power is just 1 divided by the focal length. The only trick is, for this to work, the focal length has to be in meters. That's a key detail. And what do we measure this power in? The unit is called a diopter, and we just use a capital D. So a lens that has a focal length of exactly 1 meter has a power of, you guessed it, 1 diopter. This is the universal standard that eye doctors and opticians use everywhere. And this is the moment it all connects directly to your life. When an optician writes out a prescription for glasses, that number they write down isn't just some random value. It is the power of the lens, measured in diopters. It's a direct application of the physics we've just been talking about. So let's decode a real prescription. Let's say it's plus 2.0D. What does that mean? Well, the plus sign tells us it's a convex lens, the kind used for farsightedness. The number 2.0 is the power. We can even work backwards to find the focal length. It's just 1 divided by 2, which is 0.5 meters. And if the prescription was negative, well, that would just mean it's a concave lens for nearsightedness. It really is that straightforward. So there you have it. From seeing a bus in a tiny car mirror to the glasses sitting on your face, it all comes down to the same elegant math. We've just decoded the physics of seeing. And it kind of makes you wonder, right? What other everyday things are secretly being run by a simple, beautiful little equation?